goal of the Sensor Network project was to create a system that was both modular and scalable, allowing us to change certain parts of the system while leaving the rest untouched, and to adjust to a variety of different needs, whether it be one sensor or multiple sensors. The wireless nodes of our sensor network are these hexagonal PCBs. On each one you'll see a 3.3 volt regulator, a 5 volt regulator, a 6-pin header for programming, broken out reset and flash switches to facilitate programming, 6 DB9 connectors to allow a variety of sensors to be plugged into the boards, an ESP8266 wireless chip providing 802.11b wireless connectivity, various support components, an I2C bus to allow all the sensors to communicate back to the ESP8266, and a handful of status LEDs. The sensor modules in this system are small PCBs, each containing one DB9 connector, its own microcontroller, its own set of programming pins, and whatever sensor it's intended to integrate into the system. In our case, we chose to use the Atmel 328P microcontrollers due to their support in open source programming software and their good documentation. But any microcontroller should be able to be used with this system, provided that it can communicate over I2C and can be powered by either 3 or 5 volts. The reason each board has its own microcontroller is because each board is generating a JSON object that is used by the database sitting on the server directly. The rest of the network is completely unaware of what is actually being transmitted. This also allows specific boards to be programmed to handle specific incoming information, whether it's PWM, I2C, SPI, or an analog voltage. The onboard microcontroller is then responsible for taking this incoming signal and producing a human-readable output. By making the microcontroller responsible for this portion of data collection, it allows the server to not have to worry about what kind of data it's receiving. It can simply integrate whatever it gets, put the appropriate labels on it that are included in the JSON object, and move on, allowing the user to easily access it later and know what it was receiving. To program the sensor node, use the FTDI cable and plug it into the 6-pin header. Then hold the reset button, press the flash button, and then release the reset button. Plug the other end into your laptop and you're ready to go. For programming our hardware, we chose the Arduino IDE because it is free, cross-platform, and it's just very simple. It doesn't have a lot that can go wrong with it. Once the board profile for the ESP8266 has been installed, you can create a new file or open an existing one, make sure it compiles, and load it onto the board. For the networking in this project, we're using an open source library written in C that supports the ESP8266, giving us access to various wireless modes, as well as encryption and things such as TCP and UDP for higher level network programming. While in its current state, we didn't need anything more than what the Arduino IDE had to offer. The project also supports Platform.io, which provides much more in-depth IDE capabilities such as unit testing, multi-board integration, and version control. The server we're using runs Ubuntu 14.04 and MeanStack, which includes MongoDB, Express, Angular, and Node.js. We chose Ubuntu 14.04 because of its stable, long-term release cycle. We decided to use MeanStack because JavaScript is lightweight, and MeanStack provided us with end-to-end JavaScript. It uses it for the database, uses it for server scripting, uses it for the web app front end, and since the sensor modules, the furthest point from the server, are generating JSON objects on the boards, we're even using it in the data collection portion of the process. The reason we went with DigitalOcean for our server hosting was because they provide virtualized high availability servers at a very low cost, and they were very flexible, gave us root access. We could treat it just as if we had the hardware right in front of us. And ultimately, for the duration of the project, it ended up being cheaper to host with them than it was to have our own hardware here, and we avoided all the headaches. The web app is built on Angular. This is part of the full stack JavaScript solution we went with for this project. Using JavaScript provides us with some advantages over using just simple HTML or CSS. By utilizing the Angular framework, we get a web page that updates as new information becomes available without having to click the refresh button or having to do some special coding or embed anything fancy. The framework is built to do this dynamic updating. This is particularly handy for our application because new sensor data is becoming available all the time. The graphs need to be updated constantly as new data arrives. The status of the nodes, of the modules, they all need to be updated. We need to see where everything is at, how much power it's got left, and all these things can be done in one single web page where the user never has to change what they're doing. They never have to hit the refresh button or worry about the information they're seeing being out of date. It's always up to date, and that's just built into the framework. Looking at the web app itself, we see basic functionality, a list of all available nodes, current status of those nodes, all the historical data they've collected, as well as some configuration settings. It's fairly basic, but it does prove the concept and allows us to retrieve the data from the database. For this project, all our testing was done manually. Hardware testing checked input voltages as well as connectivity for communications. Software testing checked the functionality of each piece of the code as it was integrated into the larger project. Hardware testing concluded that a minimum input voltage of 3.9 volts is required in order to activate the ESP8266 modules and create a wireless connection. It also determined that if input voltages ramped up too slowly over the course of several seconds, that the modules will lock up and reset switches will not work. You have to cycle the power to them in order to recover from that state. In terms of communications, the Wi-Fi modules were tested after the reflow oven to ensure that they were still working, and the I2C bus was checked on all of the ports using working sensor modules to ensure that communication was functional. Software testing came down to functional testing of the final product, showing that it performed as intended. Ultimately, we succeeded in creating a modular and scalable sensor network. While we did not end up producing as many different types of sensors as we had initially intended to, we did create a strong foundation and a system that is easily adaptable to all those types of sensors and many more. Should we decide to continue working on this project in the future, some of the main things that we would like to do that we didn't get a chance to do were reducing network latency, adding wireless clock synchronization, adding in micro USB programming support to the sensor nodes and sensor modules. and possibly changing to a different wireless chip on the sensor nodes themselves to further increase their range, their power efficiency, and how well they can communicate with multiple other nodes in the network.